Oh, thank you very, very much. Now for the... Great. And now, sorry to say, for the English portion of the program. I was listening to the earlier remarks and heard the word mathematics many, many times. And I think I heard my name at one point. So I would first of all like to thank the Center for the Promotion of Science and the people who have done such a nice job of organizing this, inviting me, and making me feel welcome. This is my first visit to Serbia, to the Balkans in general, and it's been just a wonderful, wonderful delight. I will say my talk, as you can see, is in praise of not paying attention, and I really do hope that many people in the audience will take that quite seriously. In fact, earlier there were some students up here who were working on a couple of puzzles that I had brought along, and I would invite anyone who wants to come up and work on them while I'm talking and not pay attention to the talk itself. The reason I titled this is, as it may or may not have been explained, I've worked for the last 30 years as a freelance mathematics writer. I report on things going on in the mathematical sciences. I hope I can be heard okay, and I'm not speaking either too loud or too softly. Indicate your displeasure when you experience it. But over the years, because of the work that I do, I go to many, many, many math conferences, go to many talks that are way over my head, and I frequently over the years found myself just my mind drifting off because I'm not following the speaker, and just playing around with some ideas that I've either had for a while or sometimes are inspired perhaps to think about during the talk itself. And I've actually, from time to time, come up with things that do seem to be of some interest. I should say most of the things that I come up with are not of interest, but hopefully you won't be seeing any of those tonight. And my computer is being a little recalcitrant for the moment, but I think it'll start. Good. First things first, I really do want to give thanks to the Center for the Promotion of Science and to the Mathematics Institute here for the invitation and all the arrangements. And I'm going to have to try again. We'll see if it goes on. Just a very brief introduction again to explain what it is that I do as a mathematics writer. I've frequently been asked this, and I finally found a couple of quotes that I think encapsulate my experience as a journalist, but although they were said generally of people, and naturally I'm going to have trouble with this. We'll try it one more time. Okay. Lord Northcliffe, who was the founder of British tabloid journalism a long time ago, said, "Journalism is a profession whose business it is to explain to others what it personally does not understand." This has very much been my experience reporting on mathematics that is difficult for me to understand, and I need to get it across to other people, and doggone it, we'll try it. May have to restart. Okay, whoops. I'm sorry. Beg your pardon. This is, I've given this talk now. This is the fourth time I've given at least parts of this talk, and you can see I'm still perfecting it. G.K. Chesterton, a British writer, said, "A journalist is a person who works harder than any other lazy person around," and that, I think, describes me as well. One of the things that means is that I can oftentimes take a day off, an afternoon off, pick up a novel, read it, and consider it professional development, because I'm always trying to learn how to write better. And I frequently run across instances of mathematics in works of literature. And I'd like to give one example, which I really enjoy. There was a collection of poetry by an American poet, Sandra Gilbert, that came out about 20 years ago, called Kissing the Bread. I saw it in a bookstore, picked it up to see poets frequently do have poems about mathematics in them, and I thought maybe she does as well. It turned out she had an entire section of poetry about mathematics. The section was titled after one of the poems, called When She Was Kissed by the Mathematician. Now, the poem is about a page and a half long. I'm only going to read the first 2 lines. Starts, the morning after the night she was kissed by the mathematician, she woke with a new intelligence. Now, I asked my wife if that had been her experience, and she said she did wise up, but by then it was too late. At any rate, what I'm going to be talking tonight about really is just fun mathematics, or math that I've found fun. But I do want to stress that mathematics is serious business. It's really, really important in almost everything we do today. From finding cures for cancer, mathematics is needed in modeling what goes on, to understanding and addressing issues of global warming, global climate change, to designing the next generations of computing systems and the interconnected webs that are involved there, to simply understanding what the universe is made of and where it came from. Okay. But math is also fun, and that's what we're going to just do tonight, or hopefully. And in this, I take as some of my models Martin Gardner, who wrote a mathematical games column for many years for the American Scientist, mathematician Richard Guy, who is now 102 years old, is still doing mathematics at a pace and a level that puts me to shame and many others. John Conway, who's famous worldwide for something called the Game of Life, but has done many, many other great mathematical discoveries, but will take almost anything mathematical seriously and have fun with it. Okay. And finally, a bit younger is father and son team, Eric and Martin Domain. Eric is the son on the right. They're at MIT in the computer science department, and they play with all kinds of stuff and are making wonderful, wonderful discoveries. And this is a signal to me that I'm going to skip to a different segment, okay, and start with something that I came up with quite a few years ago, playing around with something called gray codes. Now, gray codes are an important thing that happens in computer science and discrete mathematics. They're named after Frank Gray, an American engineer, although they could have been named after an English 19th century engineer, Emile Baudot. What they are is they're a particular way of listing all the n-bit numbers. And an n-bit number is just a string of zeros and ones of length n. So, for example, if you have 3-bit numbers, okay, what is essential in a gray code is when you go from one number to the next, you only change 1 bit. So, and at the end, you want to cycle back to the beginning. So it's common, generally, to start with all zeros, change one of the zeros to a 1, then change another 0 to a 1. And you can see in there, hopefully, that at some point you've got all 1s, and then you start chipping away back to the bottom where there's only a single 1, which allows you to go around to the top. Here's just another quick example, 4-bit numbers, which are the ones that I'm going to focus on. Again, just starting at 0, turn one 0 into a 1, another 0 into another 1, and go on. You can see, again, all ones happen at some point, and then you get back down to a single one which wraps around. There are many, many different ways to arrange 4-bit numbers. I've only shown you one that has a specific pattern to it. And it's an interesting subject in itself to look at all the different ways you can do this. What I wondered was if I could do something a bit artistic. And if you're going to do art, you need a canvas. And I'm going to work with 4-bit codes. So I'm going to divide the canvas into 4 triangles, okay? And I'm going to put bits in each of the little triangles. And so just to start, we might as well start with all zeros. And now, okay, to do something really artistic, I'm going to color code this. And since 0 is nothing, and black is the absence of color, I'm going to color the zeros black. So I'll just color that black, and that black, and that black. And there, I've done something artistic. Okay, well, I mean, you might ask, but is it art? I will argue, yes. You can go to the Museum of Modern Art in New York and see an all-black painting, okay, that's worth millions of dollars, I think. Now, there's a little more to it than that. But seriously, what I really mean to do here is I want to get all the different combinations of zeros and ones, okay, into a 4x4 array of squares. And the idea is that I want each pair of adjacent squares to somehow differ in just one bit. So the rule I'm going to use for adjacent squares is, let's say we've got all zeros somewhere, and I want to know what should I put next in the square next to that. The rule that occurred to me is simply reverse the bit in the triangle that's right next to your square, and then mirror image everything else. Okay? So when we do that, we get something that looks like that. A single one right next to the zero. So if you think of a vertical mirror there that somehow perversely distorts and reverses everything that's right up close to it, but shows everything else okay, that's what we've got. Well, the question that occurred to me is, well, is this rule consistent? Meaning, and the answer is yes. I don't know why I put it there. Meaning, suppose we've done that with a vertical mirror to get the square on the right. It's my left. And also vertically, down. Put a horizontal mirror and reflect that upper left-hand square down. The question is, what do we do about this lower right hand? There are 2 ways to get there. Okay, we could either come across from the left, or we could come down from above. And there's a little worry that you might get a different result depending on which way you come, but in fact you don't. You can see that either direction you come, what's adjacent to the square next to it has been reversed, and everything else is a mirror image. So this is what this was simply the idea I had. So let's look at the whole shebang, just everything. If I start with all zeros in the upper left, and we'll see that doesn't matter, you get this pattern of ones and zeros. What's a little bit remarkable here is actually you have all 16 different combinations of zeros and ones, okay, in the various different triangles. And so we really are looking at, all the 4-bit numbers in some sense, and arranged in a way that is kind of like a gray code in that things that are adjacent differ in only one way, okay? Well, the thing to do is color this. So let's color the zeros black, And now let's clean it up, get rid of the ones, and now let's even get rid of the guidelines. And we have something that starts to look a little nice. And you can also notice that the far left-hand edge is solid black. The far right-hand edge is solid white. The same with the top and the bottom. Solid black on the top, solid white on the bottom. And that means we can tile the plane. And when we repeat it like this, we get something that looks kind of nice. And I'll reduced it here to show a bit more of the pattern. It has kind of a quilty sense to it. And when I first did this by hand, I had a scribbly little drawing that it looked okay. But when I finally drew it on a computer to get things, really crisp and neat, I thought I'd done something really nice. It was nice enough to make the cover of Mathematics magazine about 20 years ago, in part because the editor was a friend of mine and he needed something for the cover, but nonetheless. Okay. Having done that, I thought, why stop there? Let me just play around with the rule. What I really now wanted was, 4x4 array, and I want to get all 16 combinations somewhere in that array. And I do like this notion that you always have black against white, either right and left or up and top. And so I came up with a second rule, which was reverse everything except what's furthest apart. In this case, the furthest left, that 0 in the furthest left, should stay as 0 when it's reflected on the right, but all the other zeros become 1s. So this is an alternative rule. It's no longer got anything to do with gray codes, okay, as far as I know. Maybe it does, But it turns out this is also consistent, meaning doesn't matter in what way you get from one square to a next, the rule always gives you the same pattern. And in this case, here's what you get, except I realized, having done it, I made a mistake. There's a 0, I'll point to it. That 0 should be a 1. And that was my mistake, and it was easier to correct it this way and get rid of the oops. At any rate, that's what you get. Again, this rule, which acts purely locally, just, this is one square, this is what you get next to it. But if you faithfully pursue it, it actually produces all 16 combinations. Okay. Why it does that, I can't really say, but it does. Okay. And when you color code it, that's what you get for the black, and that's what you get when you remove the guidelines and the ones. And it turns out it also tiles the plane and comes up with a pattern like this. And just to remind you, this was the first pattern, and this is the second. And they have some similarities, but they actually have quite different appearances. Okay, so to explore on this, and this is where I hope people will stop listening to the talk and start maybe doodling or at least thinking about it. There are certainly other 4x4 rules. I came up with 2 on my own, okay? But there ought to be other rules that still produce all 16 combinations. Or forget about rules, just say, look, I want to put all 16 combinations in a 4x4 grid, okay? Now, my basic premise is I always like to have a reversal from black to white when you go from one square to another, either horizontally or vertically. I mean, do whatever you want. In fact, why use squares at all, okay? You could certainly think about doing this on a hexagonal grid or a triangular grid or a pentagonal grid if you can draw one. I tend to stick with square grids because they're easy to draw and I find them easy to think about. One can also certainly do things with random patterns and see what comes out of that. Or certainly better colors. I tend to stick with black and white because I'm frequently writing on a piece of paper with a black or a blue pen during a talk, and it's hard to switch from one color pen to another because I usually only have one pen at a time. Or more colors. Again, gray codes come out of our binary digital era of zeros and ones, but there are many more numbers than 0 and 1. And so perhaps having more colors would be of value. And that's my sign to go elsewhere. And I haven't gotten anyone to come up with here, but maybe that's for the best. Okay. This next problem I'd like to talk about, again, is something that occurred to me while I probably should have been working, but this turned out to be probably more interesting than whatever I was working on. Something I called the Solid Wit Problem. And we've had it up here, and there are handouts for this problem that I encourage people to pick up. This came from a book that I picked up at a used bookstore. Solid Wit, should say, is an American artist, or was an American artist. He was one of the founders of the so-called conceptual art and minimal art. He did a lot of paintings and sculptures and drawings and so on. He's famous, he's quite well known for large-scale wall paintings, such as this that was at the Metropolitan Museum in New York. Actually, no, I think it's a permanent piece there. You can see he's influenced strongly by geometric objects and ideas. Here's another piece that's got very colorful geometric panels with a big black, possibly fractal type, fractal-inspired blotch on it. A large wall drawing of straight lines that's at the Whitney Museum that actually I just recently saw. He's also known for sculptures, again with very strong geometric aspects to them. Here's one, he likes to do cubes, okay, in many of their different ways, okay. And then he has many drawings and etchings, again with strong geometric and some combinatorial flavor to them. There's one, have some that have squiggles, although there's some geometry underlying even those. And then there's this piece, which is what I found in this book that I picked up, that was an exhibition catalog. And I hope you can see it there clearly enough. It's called Straight Lines in 4 Directions and Their Possible Combinations. And I will skip to a redrawing of it here and come over. And what LeWitt decided to do was take horizontals, verticals, up diagonals, and down diagonals, one at a time across the top. The next row and a half is the 6 combinations of them 2 at a time. And he sort of likes to always start with a horizontal, and then vertical, horizontal up, horizontal down, and then he does vertical up, vertical down, and so on. And then he does the combinations 3 at a time, and then he does them all. And then what he had or at least the book had as the title, is clearly meant to just be an empty square. So each square, it's a bit like a gray code, actually, in that each square either does or does not have a horizontal line, a vertical line, an up diagonal, or a down diagonal. Okay? And there are 16 combinations of those, and he's put them in a particular arrangement that makes logical sense. But when I looked at this in the book, I noticed, and perhaps you've seen it as well, certain horizontal lines continue from one square to another, but they don't make it all the way across. Here, though, is, if I can find it, yes. Here is a diagonal that starts at one edge and does make it all the way down to another edge. here's another diagonal right here, this short one, and then, you know, a nice easy one down here and another one up here. But in general, even as diagonals, they don't make it all the way across. You know, here's a vertical that doesn't make it to either edge, okay? Well, but that's just because that's how Solid Wit arranged them, according to the logic of, you know, taking them, you know, in a particular order. Incidentally, here's what it looks like when you remove the guidelines. And you know, I only did this for this talk, and I was actually quite struck by what a different look it has compared to this. And I rather like the look here. It has kind of a runic quality to it. Here it is in wood, which is the puzzle version I brought along, which I always enjoy bringing and showing people because they think I made it. And I have to say, I did not. A friend of mine in where we live, who's a retired mathematician and a master woodworker, has done both these wooden puzzles. Notice that when you rotate the board, you still have all 16 combinations of horizontal, vertical, up and down, diagonal. You can keep rotating it, and it comes back to the same thing. The question that occurred to me was, can we rearrange the squares so that all the lines do go all the way from one edge to another? So LeWitt had it arranged in a sensible way, but didn't have the property that I wanted. Okay, and so I was actually sitting in my basement office with this book, and this problem occurred to me, and I cut out a bunch of little squares of paper and carefully drew all 16 combinations. And that took a little doing, because you have to keep track of which ones you've done and which ones you still haven't. If you take one of the yellow or gold sheets, you will not have to do that. They've been done for you. And then I started playing around with it, and we'll show you what one might do as an attempt to arrange things. Here I have completed a horizontal line, so I'm happy. And now I've completed a vertical line, so I'm happy. And there I've completed 2 diagonals, so I'm still happy. But as you can perhaps see, this next piece really has nowhere to go. So my attempt to solve this has gotten stuck. Okay. And you can perhaps see that the piece that I'd like to fit in has actually both a horizontal and a vertical line, but everywhere I put it is going to be in a row or a column that already has squares that do not have horizontal or vertical lines in them. And so that piece really does have nowhere to go. In fact, you may have noticed that I shouldn't have put this piece here to begin with, or one of the pieces. There was going to be a problem because this diagonal would want to go through this piece here. So I probably shouldn't have put that piece there. Maybe that was my mistake here. Okay. Now, in some versions of this talk, well, let's see what happens. Okay. So I encourage people, make your own and try it, or pick up one of the sheets and try it. Incidentally, on this, I put these little circles to indicate kind of an anchor that discourages rotation of pieces. And the reason for that is if you rotate, for example, a horizontal piece through 90 degrees, you actually get 2 vertical pieces, and you don't have a horizontal. So it just means that Solid Wit's arrangement of all 16 combinations is broken up, and you've got duplicates of things. Okay. Now, that's, neither here nor there. Okay. You're certainly free, as far as I'm concerned, to rotate pieces. In fact, I always encourage people to do anything but what I tell them to do, which, when I think about it, is a bit of a contradiction in itself. If you allow rotations, it certainly gives you more freedom to get things started. Okay, it gives you more possibilities, more freedom, but it also makes life harder in the sense that there are more possibilities to consider. And so what happens is, if you think about looking for solutions as looking for a needle in a haystack, by allowing rotations, you may allow other ways to solve the problem. So you may get more needles to look for, but your haystack becomes much, much larger. Okay? And there's always a tension between those two. Okay? And again, or have a woodworker friend make you one out of wood. These are a couple of students at the college where we live who were working on this unsuccessfully, as it turned out. Things to look at here is, how many solutions can you find? Okay, that's always an interesting question in mathematics. It turns out there's a surprise in every solution. And I'm not going to say what the surprise is, because it's more fun to discover it for yourself. The solutions have a rather amazing property. And the real question is, where did this surprise come from? Okay, and I'm not going to say what the surprise is, nor am I going to show you a solution, because you can try this for yourself. But finally, okay, this is just something that occurred to me. Okay, there ought to be other similar problems, maybe with surprises of their own. Okay. And a couple I'll suggest are one I call the circle Wit problem, where what I've done in this case is either drawn or not drawn a quarter circle centered at the corners of a square. So across the top, I've got a circle in the upper left, upper right, and bottom left. You can even see a little organization there. And then the pairwise combinations, and then 3 at a time. Then all 4 corners have a quarter circle, and then you don't have anything at all. So I've tried to organize it a la Solid Wit. And again, removing the guidelines, it has sort of a nice pattern. The question that I would raise here is to rearrange things here to try to make complete circles, okay, whenever possible. Again, I would say don't rotate, but you're free to do with it as you please. Another problem that occurred to me more recently, just a few years ago, which are these magenta handouts up at the top, is something I call the sine Wit problem. And my question here is to rearrange things to make sine waves. Each square either, again, does or does not have a half a sine wave along each of its 4 edges. So here you have one across the top, across the right, across the bottom, across the left, then the pairwise, then 3 at a time, again all 4, and again nothing at all there. And what I would like is to be able to go all the way from say the right, up, down, up, and I'd like to have a down one there. So rearrange things so that you get a nice undulating sine wave all the way from right to left, all the way from top to bottom. Or do something else. Actually, that's my real message. What I'd really like to see is somebody come up with something really interesting to do with this design. And again, here it is with the guidelines attempted to be removed. And I'll give you one little hint. Remember those 2 gray code patterns that I came up with? These guys from before. It turns out one of these actually is a solution to the sine Wit problem. And the question is, you know, is it that one on the right, okay, or is it that one on the left? And I'm going to leave it at that as to what it actually means at all. Again, here, either the take-home questions or the stop listening to the speaker question is to ask, are there other interesting math problems in other works of art? Okay. Or, more interestingly, can you turn math problems into their own interesting works of art? Okay. And I think we'll go from there. And do I have time for one more? Yes, okay. Okay. This last one, speak about what I call the bricklayer's challenge, and it refers to this wooden puzzle up here, which a few people were working on earlier. It's also known as building barricades. This is the name given to it by Richard Guy, the 102-year-old. He was a spry 90-year-old when I showed him this problem, and he came up with the name. He likes plays on words, and I'm coming to like it because it might be my one chance to have my name associated with something. Also, I like to call it I'm no Gauss, because the problem comes from an old story about the mathematician Gauss, okay, the early 19th century. He actually used to tell this story. As an old man, he would tell this story to people, and so it has some basis in fact. The story is, as a young child in grade school, the teacher assigned the class some sort of arithmetic problem to keep them busy. And in many versions, it's common to say the teacher told the kids, add the numbers 1 to 100. And the story is that Gauss, okay, solved it almost immediately. Okay. And it's not clear, for one thing, what the problem actually was, nor is it clear exactly what Gauss did. Okay. But what Gauss could have done with this problem was notice that, well, if you're adding the numbers 1 to 100, you can add them backwards, okay, and you'll get the same sum. Okay. It doesn't matter in what order you add numbers. But if you have them lined up like that, you can combine 1 with 100, 2 with 99, 3 with 98, and think that, well, you've got the number 101 a whole bunch of times, and that'll add up to whatever the sum you are trying to get. If you add a bunch of 101s, you'll get twice that sum. That's what the 2 question mark means. And just notice that, well, how many 101s do you have? You've got 100 of them. And so the sum that you want is just half of that. So 101 times 50, and that's 50-50. And as the story is, Gauss didn't write any of this down. He just saw it in his head. He wrote down the answer 50-50 on his slate little tablet and slammed it on the desk where the teacher lay. Made a sound like that and said, "Liget ze, there it is." Okay. And the story goes on from there about how the teacher was impressed with how smart young Gauss was. At any rate, some years ago, actually a friend was collecting versions of this story with the details about, you know, was it a cold morning? Was it a dark, dank schoolroom? Was it a tyrannical teacher? And so on and so forth. There's an interesting kind of tree of stories as people have embellished it over the years. And he was also interested in collecting different ways Gauss might have solved a problem like this. And that caught my eye, and I asked, well, how would I have done this? Okay. How would I have solved this problem if I were in Gauss's class? Not his class as a mathematician, but his school class. Okay. And it occurred to me, that's the problem again. Well, I would have done this. So it started with 1, then added 2 to get 3, added 3, got 6, added 4 to get 10. I would have ploddingly added each number in turn, and I'm going to stop there, okay? Let's do this with a slightly shorter problem, adding the numbers 1 to 4 to get 10. And what I would have done would have been this, and I would have stopped with each addition and kind of admired what I had accomplished, and also checked it to make sure that I hadn't made arithmetic mistakes, because I commonly do. And then I thought, well, you know, one thing to be absolutely certain, or a little more certain that I haven't screwed something up, remembered that, well, it doesn't matter what order you add numbers, you should always get the same answer. And so I would have tried it in a different order. I would have started with 2 and added 3 to get 5, and then added 4 to get 9, and then added 1, and yes, I get 10 again, and I'm happy. What I observed, in part because I was doing it on purpose, was that in these two problems, in the first problem, you get the partial sums. You start with a 1, and then you get the partial sums 3 and 6 before you get to 10. Whereas in my second approach, I started with 2, and then I got the other partial sums 5 and 9, and they are different than I had before. That was partly on purpose, but as soon as I saw that, I thought, well, can I do it again? Can I find another order in which to add the numbers and get the other possible partial sums? And I saw, yes, I can do it. If I start with 4 and then add 3, I get 7. And if I then add 1, I get 8. And then add 2 and you get 10. And the partial sums here are 4, 7, and 8. And so what we have is all 9 partial sums once and only once. And again, there's something along the lines of the gray codes and the Solid Wit. You've got all these combinations once and only once. Mathematicians, especially combinatorially minded mathematicians, really like the notion of getting things once and only once, although then they use the same idea over and over and over again. At any rate, so quickly ask, God, can I do it for 5? Can I add the numbers 1 to 5, which I know gives you 15? Well, it took me quite a while to discover that you cannot. Okay? And the reason is quite simple. Each arrangement gives you 4 partial sums before you're adding 5 numbers, but the 5th number gives you the final 15. So you only have 4 partial sums along the way. But there are 14 partial sums less than 15. And as you can perhaps already see, 4 does not divide 14. So if you get 4 and you get another 4 and you get another 4, then it just doesn't work. Okay. So, okay, might have quit there, but said, doesn't work. Let's go on. Okay. Never stop when something doesn't work. Just thought, can you do it for 6? Okay. And the answer here is maybe. Okay. Because now each arrangement gives 5 partial sums before you get to 21. And there are 20 numbers less than 21. And 5 does divide 20. So at least there's a chance. But, can it actually be done? And here, again, I just started messing around and seeing what would happen. And fortunately, it worked out, and I found an answer. And there it is. Okay. These are 4 different orders in which to add the numbers 1 to 6. And if you have to really look at it a long time to see that every number from 1 to 20 is somewhere in that list of partial sums. And of course, you also need to check that I've done all the arithmetic correctly, but let's not worry about it. It really does work. I've actually checked this, I think. No, I haven't checked this, but I'm pretty sure it works. Okay. At any rate, now, having succeeded with 6, can you do it for 8? We're skipping 7 for the same reason we had to skip 5. It just turns out that if you try to work with all the numbers up to 7 or 9 or 11 and so on, you get the same problem as we did with 5. So the problem really only makes sense for even numbers. In the case of the numbers 1 to 8, we wind up looking for 35 rows, 35 different orders. Each order has 7 partial sums, and 7 times 5 is 35, which is 1 less than 36. So it is at least possible. And again, the answer is yes. And I could show you, an answer, but it would just be a jumble of numbers and not really worth looking at. But as soon as something works for the first few examples, okay, when you skip over the examples where it doesn't work, okay, it raises the question, can you do it for any even number? So anything up to 2n. If we add the numbers 1 up to 2n, turns out the sum is 2n plus 1 times n. That was actually Gauss's 10-year-old insight, or insight as a 10-year-old child, roughly. And a little bit of mathematics. We're going to be looking for n plus 1 rows. Each row should have 2n minus 1 partial sums, okay? Because you're adding the numbers 1 up to 2n, so you've got 2n minus 1 things before you add the final number to get the actual sum. And it just works out. The critical thing, if you take away anything from this talk at all, is that this is an unsolved problem in general. Okay, and if there's something worth thinking about for students or anyone afterwards, it's to see if you can make some progress with this. I'll tell you what's known, at least the last I've heard. There certainly are solutions for all the even numbers up to 26. And then for technical reasons we'll go into, they started skipping over the multiples of 4, and they found solutions for 30, 34, and 38. This was done about 8 years ago it was done by computer search, and the programming was done by a fellow named Rob Pratt. Just last year, I got an email from someone in Heidelberg, as it turns out, who's extended that computer search to all the even numbers, again, skipping the multiples of 4, all the way up to 110. And by the time you're there, you've got something like 56 rows, I guess. It's a big, big, big problem. And the only reason I think they stopped at 110 is just after a while, the computer search just gets too slow to justify. Now, let me explain why or try to explain why they skipped the multiples of 4, and also where it got this name, the Bricklayers Challenge. And that's where this wooden puzzle comes in again. And also Richard Guy played a key role here in what he called building Barricades. He said, if you have a solution, picture it as a wall of bricks. And so let's look at this, okay? And this actually is that earlier solution for the numbers 1 to 6. And what you have is each row has bricks of all lengths, 1, 2, 3, all the way up to your even number, in this case 6. And you can actually see across the top there, they're in the top row, everything is in order, and the other rows are a bit jumbled. Okay. The point is that there are no seams between horizontally adjacent bricks. They are vertically aligned. And so let me go over here. There's only, this seam doesn't align with anything. Here's one that, drops down here and so on. And what's going on is these seams are the partial sums. this is 1, 3, 6, 10, 15, 21. Here's 2, 7. This must have been 2 plus 5 is 7 plus something, probably 4 is 11, and so on. At any rate, the notion of partial sums gives way to this really lovely geometric interpretation, to the point that when it's presented as a puzzle, my friend Lauren Larson, who made the puzzle, and I have taken it to various little events and had young kids, 4-year-olds, 5-year-olds, 6-year-olds, okay, working on this as a geometric thing, and they actually have better luck than the adults, and so on. Now, let me just run through. For, you know, the simplest thing you can possibly do, that's it, okay? The case we've already seen, there was the thing that I did earlier, okay? It turns out there are 2 more solutions that look like this, okay? And it's a little difficult to see they're different, but one way you can see it is in the top one, the top row has the numbers in order, 1 plus 2 plus 3 plus 4. The other 2 do not have that anywhere in any of the rows, either forwards or backwards, okay? And so they certainly are different from the top row, and they also differ from each other, okay? Here's that solution for 6, okay? Here it is in wood, and you can see it for yourself at the top if you come up. Now, to explain very quickly why we skip the multiples of 4, it's a notion of rotary barricades. This, again, is Richard Guy's name for it, although the basic idea is quite simple. So here's a solution for 2n equals 6. Let's duplicate that. Now, if you have a solution, okay, you can certainly rotate it through 180 degrees, okay, and it'll still be a solution because you don't suddenly have seams that align, and you also still, every row has all the bricks from length 1 to 6. But certain solutions, when you do that, don't change, okay? And so the idea was, or an idea is, if you're going to try to have a computer search for solutions, basically the computers just start, you know, messing around and just try something. They do something that computer scientists call depth first search. You try the easiest thing, and when it stops working, you come up and try the next, you know, harder thing. And when that doesn't work, you can come back and so on. In the case of building the Bricklayers Challenge, the tendency is to work from left to right, and to a certain extent from top to bottom. And it generally makes sense to, you know, put your, you have to have a brick of length 1 somewhere on the left because you have to pick up that seam. You also need a brick of length 2. You might as well put them in the top, and you might as well, because if you have a solution, you can permute the rows. You might as well, you know, have everything increasing on the far left, okay? And then you just start trying stuff and seeing what you can do until you're forced to have a seam, and then you backtrack a bit and try something else and go forward. The advantage of working with these rotary barricades, these symmetric solutions, is that whatever you do on the left, you do the same thing on the right, just rotate it. And so as you're trying things out, you're coming in from both sides, and you run into trouble more quickly. And so you have to do a little less backtracking, okay, and then try something else. And now, the problem with this is there might be solutions but there might not be any of these rotationally symmetric solutions. So the computers have been saying, or the programmers, it's not, the computers haven't taken over completely yet, but they decided, it would be quicker to find a rotationally symmetric solution, so let's try that. They've tried it. It's always worked as far as they've taken it. Now, it might stop working at some point. Who knows? Okay. So these rotationally symmetric solutions, it turns out, can only exist if you have an even number of rows. And it turns out when you're dealing with a multiple of 4, you have an odd number of rows. And so that middle row gets rotated still as the middle row, and so it cannot be the same because it'll be the same bricks but backwards. Okay, and so it cannot be symmetric. They may not exist even when you have an even number of rows, but they do up to 110. We know that so far. Okay, and as I said, when they do exist, they're easier to find. Okay, so the computer searches go more quickly. And I'm sorry, I'm going to skip over. No, this will only take a minute. There's an additional condition that's worth thinking about that's called the Fink condition, named after a student of Richard Guy's named Alex Fink, standing next to some sort of a brick wall. It's more of a stone wall. His observation was that if you divide your wall into, in this case, 3 parts, 2n minus 1 parts. So at any rate, you divide it into equal parts, then each row has one seam in each part, or at least this solution does. Okay, so there's a seam in this left-hand part, a seam in the middle, and a seam in the right-hand part. The same thing for the second row, the same thing for the third. Or you can think of it as each section has one seam in each row. The first section has them 1, 2, 3. The next one has them 1, 2, 3, 1, 2. And the next one has it 1, 3, 2, something like that. And Alex noticed that, some solutions have this property. Most do not. But again, it's something that could be used to shorten the search and make it possibly go a little bit more quickly. We'll end with some open questions. Again, are there solutions for all even numbers? That's really the key question. Okay. Are there always solutions that satisfy this Fink condition? And are there always rotationally symmetric solutions when it's possible, when you have an even number of rows? In other words, when you're not a multiple of 4. And finally, how many solutions are there for each even number? Now, the conjectures, and at this point these are nothing more than conjecture, but it's like more famous conjectures. Everybody who knows about this problem believes it. The answer is always yes, that there are always solutions. There are always solutions that have the Fink condition. When you have an even number of rows, there are always solutions that have this rotational symmetry to them. And I don't know if anybody's really thought about this, but there probably are always solutions that have both the Fink condition and rotational symmetry when that's possible. Finally, the number of solutions seems to grow rapidly. Now, the computer searches that have been done, they've been happy to find just one solution for each number because they're just trying to answer that first question. Can you solve it or can you not? Then the next question is, well, how many solutions are there? Okay. What we think happens, okay, is that for large values, we're looking now again for a huge number of needles, but it's in a haystack that's growing super exponentially, okay? And therein lies some of the problem. Please, if you think about this and have any luck with it at all, okay, contact me or Richard Guy or both of us. If you find a proof, publish it. Okay? And with that, I'll end. And I really thank you for all your attention. And I do invite people to come up, play with these puzzles, and I'll give the mic back to you.
I just have to say, wow. It was really inspiring talk. Thank you very much. And I'm inviting everybody to finish our journey today with mathematical puzzles here. Opet, I'm sorry, I have to finish in Serbia. Sure. Hvala vam svima što ste došli, hvala vam što ste prisustvovali ovom divnom predavanju i naravno profesor Cipra je tu da sa vama prođe kroz sve matematičke puzle koje je doneo i zagonetke i naravno nismo zaboravili pitanja na kraju predavanja, nego smo samo odlučili da to uradimo u malo neformalnoj atmosferi, tako da vas pozivam da ostanete na koktelu, da se malo družimo, matematički popričamo i matematički se zabavimo. Hvala vam.